Greetings and welcome to Distill. In the previous lecture, we had talked about the theory of linear regression, and based on minimization principle, we had derived an expression for the parameters involved in linear regression, which were beta naught and beta 1. And we mentioned that beta naught is the intercept of the line that relates y and x, the two variables, while beta 1 is the slope of that line. We had derived an expression for both of these parameters, beta naught and beta 1, which were derived by minimizing the sum of squared errors, right? So make sure that you've watched that video before you go ahead and see this video, all right? So today we'll do a very simple example on linear regression so that you know how to in uh, apply that on Python so that later on we are able to apply that for chemical engineering problems, right? But before that, uh, I want to introduce a very interesting concept, which is known as list comprehensions. And this is actually going to be very useful when we do linear regression problems. All right. So before I start with the example on linear regression, I'll start with list comprehensions. So if you remember, when we talked about accessing list elements, we said that if we have a list, say 1, 2, 3, 4, one way to access these elements is by their indices. So if I say L0, that would mean that I am accessing the element with an index of 0, which is the first element in my list, right? Now, there's, let's say if I want to print all of these elements. So I could say for I in range length of the list L, and I could go ahead and print Li, and that prints everything. That would print all the elements of this list, right? Now over here, I represents the index, which is 0, 1, 2, 3, right? But let's say I do not want to access these elements by their index. Rather, I just can access these elements directly. So, for example, instead of pointing out that, okay, I want the element of index 0, I could just say that I want an element inside this list. So we can do that by using the command for I in L. So over here, since L is having more than one entries, that is why the value of I can be all the values that are present in L, right? So instead of having allowed values as 0, 1, 2, 3, 4, or so on, which we get by using the range command, what we can do is we can say for I in an iterable data type. So for example, a list or a tuple, which we'll see later. But for example, a list in this case. So list is an iterable data type, which means that it has um, multiple datas, data inside it, right? Or um, multiple points inside it. So we can iterate over the list. So when I say for I in L, I would have all values in all possible values of I could be all possible values inside the list. So I in this case could have value 1, 2, 3, and 4. So if I print this, so in that case, I could have 1, 2, 3, 4. All right. Now, another interesting thing about lists is that you can actually create new lists by just writing a single line of code, and that is known as list comprehension. So I'll show you how would we do that. So let's say I want to create a list L1 that has all the values of list L plus 1. So for example, if L is 1, 2, 3, 4, L1 should be 2, 3, 4, 5, right? So how have we been doing this so far? We have been saying L1 is an empty list. Then for I in range L, length L, L1 dot append Li, right? Plus 1, right? And now we know that we can, instead of accessing the elements through their index, we can also access these elements directly. So another method could be, so this could be a method 1. Another method could be, we make up an empty list here and say for I in L. So now I can be 1, 2, 3, and 4. So now L2 would be appended by I plus 1 directly, right? We would just append I plus 1. So L2 would have 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, and 4 plus 1, 5 are appended to it. So this and this both are equivalent, all right? So if we run this, we will see that our L1 and L2 are the same list, right? But over here, you see, we've written 3 lines of code for each of the methods, right? Let's say we do not want to do that because, as you'll see, the lists would, your programs, as they become more and more complex, you would not want to write multiple lines of code for creating each list. Okay. So list comprehension gives us a way of doing all of it in a single line. So what we can do is, I'll call it method 3 here. We could say list L3 is equal to, now over here we have iterated over the length of L, right? We have iterated I over the length of L. So I can do the same. So I can say for I in range len L. And what did I add inside the list? I added Li plus 1 inside the list. So before my for statement, I could just write that down. Li plus 1. So what I've done is I have iterated something and I have uh, I have given whatever I was trying to append in the beginning. So this actually forms the list L3 in the same way as you formed L1. All right. So basically this entire thing has been summarized here. Okay. So in short, if I have to form a list or if I have to make a list using this method, I'll make it in a way such that I'll say list name is equal to open parentheses, whatever has to be appended, okay, for I in whatever you had written, range, whatever you had written ahead of the for statement. Okay. So similarly, if I want to use this for statement over here, so what I could do, I could say L4 is equal to whatever has to be appended. So I plus 1 has to be appended. So I'll write I plus 1 for I in, and whatever was written in front of the in command here, that is L. So as you see, the 3 lines of code has been reduced to a single line, which means the 6 lines of code here has been reduced to 2 lines. And this becomes very, very helpful. Okay. So now if I run this, you'll see L3 and L4 have been formed. Okay. And this could be very useful for, let's say, adding 2 lists. So let's say I want to make a list 5, which has to be the sum of list 1 and list 2, right? So basically, 1 plus 2, right? So for example, L plus L1 has to be done. So 1 plus 2, 2 plus 3, 3 plus 4, 4 plus 5. That has to be written in L5. So how would I do it conventionally? I would say L5 is equal to an open list, empty list, for I in range len L and L5 dot append Li plus L1I, right? That's what I would do. But now I don't need to do this. I can simply write, instead of this, I could write whatever needs to be appended. So this as it is, and then whatever we had written here, whatever was the for statement. Okay. And that creates a list L, right? Oh, sorry, L5. So now we have the list L5. Let's say if we have to multiply the two lists. So we can do the same. L6 is equal to whatever has to be appended. So Li multiplied by L6. Sorry, L1I, right? And whatever was the for state. Okay. So you've multiplied two, right? So this actually helps a lot. And let's say you do not need to store all of this in a list, but you need to get the sum of everything. So let's say I want the sum of all of the elements of L5, but I do not want to store that. So I can do that as well. So I could just say sum s, some variable s is equal to, let's say I want to um, calculate the sum of all elements of a list that is formed by multiplying elements of L6 and L5, right? So that would be, so first I'll make up a list that is uh, that is formed by multiplying all elements of L6 and L5. So that would be just L5I times L6I, right? Whatever has to be appended. And after that, whatever for statement we had to give. For I in range len L, right? And now we do not want to store this. So instead of just writing this in the form of a list, we could write sum here and we could enclose the entire thing within brackets. So this list would not be stored, but we'll be able to get the sum of all the elements, because firstly it would form this list, it would calculate the sum, and it would store the sum. The list that was formed, it doesn't matter, right? So now I've got the sum here, right? So this actually helps us a lot. So this is list comprehensions. The more you will practice, the more you will get used to these things. Okay, so you don't need to worry about it if you're not very comfortable with it right now. But trust me, as you use it more, you'll get more and more comfortable with it. When I started using list comprehensions, it was very difficult, very challenging for me. But over time, now I barely do anything without list comprehensions. This method is something that I do not use at all, unless it's a very complex program and there's nothing else I can do other than using it. Otherwise, most of the programs I write are using list comprehensions. So this is a very useful technique. Just you'll have to give it some time and you'll have to practice it a little more. All right. Okay. Now, once we are comfortable with list comprehensions, even if we are not comfortable, we'll be using it very often. So you'll get comfortable. So now, once we are aware of list comprehensions, let's go back to linear regression. So I'll just comment out everything here and I'll have this thing uncommented. So now we have 6 data points, X and Y, and we need to get the values of beta 1 and beta naught, right? So these are the formulas. As we see, we need X bar, Y bar, right? So let's calculate X bar and Y bar. So we've done this in the accessing list elements video. So X bar would be sum of all elements of the list X divided by the total number of elements of the list X. So let's just call this another variable n, because we'll be using it quite often. So n equals to len x. So this is x bar. And similarly, y bar is sum of all elements of y divided by n, right? Okay. Next thing that we need here is a summation of xi into yi. Now, if you see, we do not need a list of values of xi into yi. We just need the sum of this. So we don't need to store these values. All right. So let's say summation of x and y, summation of x times y. Let's just start with forming the list which contains x times y, right? So how would we do that? Open parentheses, whatever needs to be appended. So xi times yi. This is what we would append. And after that, we'll just write the for statement. So for I in range len x, right? That's it. The list has been formed. Okay. Now we don't need to store this list. So we'll use the sum function and enclose this list within the sum function. So now this list will not be stored, but we'll have the sum with us. All right. Now, the next thing that we need is summation xi square. So once again, we'll be using list comprehension. Let's say sx square. We do not need xi square as a list, but we need to get the sum. So let's just form the list first. So how would we do? Whatever needs to be appended. So remember, this is just one list, x. We are iterating over just one list here. So we can simply use for I in x. Rather than for I in range len x, we could just use for I in x. And whatever needs to be appended comes here. So that is xi square or just I square, right? And now once our list has been formed, we do not need to store it. So we'll use the sum function and enclose the list within the parentheses. Okay, so sx square has been formed. And now we are going to use this formula here. So beta 1 is equal to x bar times y bar. So x bar into y bar minus summation xy by n. So summation xy by n whole upon x bar square. So x bar square minus summation xi square by n, right? So summation xi square by n. And here we get beta 1. How to get beta naught? We have the formula y bar minus beta 1 x bar. So y bar minus beta 1 times x bar. So we've got beta naught here, right? So let's just do the calculation and we'll get beta naught and beta 1 here, right? Now, if you remember, we had calculated something called as the goodness of fit or the R square value, which was 1 minus sum of square of residuals upon total sum of squares, right? So let's calculate sum of squares of residuals. All right. So once again, we do not need the list of residuals or the residual uh, squares of residuals. We do not need that. We just need the sum. So let's start with forming a list. Okay. So what is the sum or basically the square of a residual? Square of residuals is y predicted minus y data or the y actual. So what is y predicted? Y predicted is beta naught plus beta 1 into xi. Remember, there are two lists here, x as well as y. So we cannot use this for I in x, right? We'll have to use for I in range x here. So this is the y predicted value. Okay. What is y actual? It's just yi. So this is the difference between y predicted and y actual. And we need a square of this, right? So this is what you would append. And then this has to be iterated over. So this is going to be the for statement. Now we've prepared the list. So we'll just use sum here. So sum this, right? And this was the sum of squares of residuals. Now, total sum of squares. If you remember, total sum of squares is given by y data minus y mean. It has nothing to do with the prediction, right? So it is y, whatever is the data point, minus the mean y, right? So we have to iterate over only a single list. So we will just use I minus y bar whole square, right? For I in y, because we are just iterating over y, right? And then again, we don't need to store this. So we will just enclose this entire thing within a sum, right? And now the R square value is 1 minus sum of squares of residuals on total sum of squares. So if I run this, I'll get the R square value here, which is 0.998. And if you remember, I had told you that this R square should be as close to 1 as possible. And this is 0.998, which is very, very close to 1. That means the fit is really good. Okay. Now let's try to visualize this fit. How good is this fit? Okay. So we can do that by two methods. First would be to plot x comma y predicted and x comma y data in the same plot. Okay. So let's start with that. So we'll import matplotlib dot pyplot, right? Now let's plot x comma y predicted, right? So y predicted needs to be created. The list y predicted needs to be created. So let's create a list y predicted. We'll again use the list comprehensions. So what is y predicted? Y predicted is beta naught plus beta 1 into xi, right? So we are going to iterate only over the list of x. So therefore, we can use directly I, right? So beta naught plus beta 1 into I. This is what you are going to append in the list. And then the for statement, right? So we have created the list of y predicted. And now we plot x comma y predicted, which is going to be a line, right? Now, x comma y data, it is always advisable if you don't have a function. So this x comma y is not a function. X comma y predicted is a straight line function, but these are just data points. So it is always recommended to plot data points as scatter plots. So we'll do that. So plt dot scatter x comma y. Okay. And let's just set the color of this to red, just so that it looks nice. And let's plot this. And you see the plots over here, the plot over here, right? This, uh, the, the data points and the line are actually very close by, right? There's just a small deviation, maybe a deviation over here and some deviation here. In most of the other data points, the line almost passes through all of them, right? So that is why we have an R square value so good, right? So this is a very useful thing to do, right? So this is one way of plotting and seeing which data point is actually uh, causing issues, or basically a good way to see how good the fit is. Another way of doing that is using what is called as a parity plot. So parity plot is a plot of y predicted on the y-axis versus y actual on the x-axis. You can change the axis accordingly. So you could plot y-axis on y actual on the y-axis and y predicted on the x-axis. You can change the axis according to your convenience. Okay, so that is the parity plot. And in that parity plot, we also plot a straight line, which is a diagonal, which is y equals to x. So we plot that straight line to see how much is it, are the data points y predicted, comma, y actual deviating from this y equals to x line, because that is what we are wanting. We want the y predicted to be y actual. So that's the ideal scenario. And the data that we have got from our model is the data points y predicted, comma, y actual, right? So let's do that. So once again, these are our data points. So plt dot scatter, and we'll plot y predicted, comma, y actual, that is just y, and we'll color them red, right? And we want to plot a line y equals to x. So we could just plot y comma y, or we could plot yp comma yp, right? Both of them are just a straight line. So anything is fine. Let's just plot y comma y. Okay. And remember, these two, this and this, these two need to be plotted in separate figures. So we'll separate them by plt.show. So now we'll be able to get two figures here. So let's see. So now you see there are two figures. The first figure is y predicted, uh, y predicted versus x, right? The straight line you see, and the y actual versus x, the data points that you see. And the second figure is y predicted versus y actual, data points as well as the straight line y comma y, right? So as you see here as well, the deviation is not as much. So that means the fit is really, really good. Okay, so then these are the two ways of visualizing. There could be many ways. These are two very common ways of seeing how good is your fit. All right. So I hope that you've understood how to use this formula in Python, right? I hope you are okay with it now. And I hope you're also comfortable with list comprehensions now. And the more you will practice, the more you'll be able to do all of this yourself. All right. Make sure to attempt the self-assessment test today, because this would involve questions from list comprehensions so that you get more comfortable with it, as well as questions from linear regression. All right. In the next lecture, um, we'll be talking about applications of linear regression in chemical engineering. So that is going to be a very interesting thing, and I'll try to get concepts from different core areas of chemical engineering to show you how the concept of linear regression can be applied to each of them. So hope you have a good time in that. And please do mention if you have any doubts with this, with whatever I've been mm, teaching in the comments section, or you could even mail me. I've put all of these details in the description, so you may look at that. Thank you.